Welcome to the next video in the Systems Programming YouTube channel or video series. And in this video, I am actually going to get started on this assignment number 9. I don't think that is exactly the way maybe I've been doing the pattern of things because we just finished assignment 8. And usually I like to do like readings first and then the assignment. But because this particular assignment seems to, the very first part of it where you do the single step, really doesn't involve anything that we haven't already talked about. And so probably it's good just to talk about this in isolation. It introduces just a few very basic things, nothing that is in the reading or anything like that. Just ways of measuring the runtime of a program and stuff like that, and using optional command line arguments and so on. So it's probably good to see that without having talked about any of the new topics because it doesn't require, any knowledge of the new topics. And then when we get down to the second part of this, which is multiple, then we're basically going to use multiple processes to recompute the same thing and see if and how that changes anything. And there we really will need the new information from the reading. So basically the plan is that I am going to show you the solution to the single now. Then when we're done with that, we switch over to the readings, talk about that until we have discussed enough to be able to solve the second part and put those, what we learned in the readings, to use. So in this video, we are starting with this assignment. So let's get sort of introduced to this assignment. So to begin with, we're going to learn about a Mandelbrot set. And a Mandelbrot set is this very interesting mathematical object. Here we're going to learn how to compute it. And it has to do with complex numbers. I guess you don't see that anywhere. Well, this is the Mandelbrot set. And so it's a collection of points in the two-dimensional plane. But really, these two-dimensional points are complex numbers. And we're not going to learn a whole lot about complex numbers in this particular video, but just maybe understand that if you have a number, like imagine you have the imaginary number I. If you have the imaginary number I, then if we want to represent that in a two-dimensional display, we would actually send that straight up, right? That's basically one unit in the y direction on the y-axis of a graph, right? That's how we sort of visually represent that. And a single real number, which is to say the number 1, would go a single unit in the horizontal direction, right? So basically the real part, right? The real numbers are associated with the horizontal axis. Imaginary numbers are associated with the vertical axis. And so if you took any number like 2 plus 3i or something like that, right? So the 2 in the 2 plus 3i has 2 units horizontally. The 3i has 3 units vertically. So 2 plus 3i would be right by 2, up by 3. So that's how you associate complex numbers with two-dimensional points. And this is an extremely mathematically rich subject. I actually personally love the subject a lot, but we won't go much more in depth than that. Now, what we do need to know is if we come up here and we look at various, so we're going to start from this formula, right? So this formula is z squared plus c. All of these are complex numbers. Z is a variable, c is a constant, although in a certain sense, we're going to be, neither one is a completely fixed constant. But in any case, so this is just take this complex number z, square it, plus the complex number c. Now, long story short, how do you compute z squared? Well, if z, we're just going to imagine that z has real part x, imaginary part y, and it turns out, right, we don't need to spend any time going through the computations if you're not familiar with this, but the long story short is that if you want to compute the square of this number z, which has real part x, imaginary part y, then the square of z has a formula. This is the formula. This x squared minus y squared is effectively what that is. And that is the formula for the new real part, right? The real part of the square. So if this doesn't make sense to you, if you don't have much of a math background, then don't worry about it, but you just have this formula for the real part. You have a formula for the imaginary part. And so we use these formulas to update the parts of the complex number. And the basic idea behind the Mandelbrot set, right? So what does this all have to do with the Mandelbrot set? Well, effectively what we're going to do is in the two-dimensional plane, we're going to pick a whole bunch of different value, points in the plane. And those are going to be our various values of C. So at any point in the plane, right? So pick an X, pick a Y, you've got a point in the plane. We're going to take that point to be the value of C as a complex number. Now, then what we're going to do is we're going to initialize the value of Z always to 0. That's where it gets initially set. So Z is 0, C is some arbitrary point in the plane, and then we apply the function, right? So with those choices of Z and C, we apply this function, right? We compute Z squared plus C, and the result of it becomes reassigned to Z, right? So you start off with Z equal to 0, but you apply the function, and the result is the new value of Z. Then you do it again, right? With the new value of Z, you reapply the function. And again, the output becomes the new value of Z. And you reapply. And the theory is that here in the Mandelbrot set, if any, because what's going to happen is you're always going to start with your Z somewhere around here at 0, basically. How do I know that that's 0? Well, I just know the Mandelbrot set. So the axes are not labeled, but I've seen this before, and I know that 0 is somewhere around here. So in any case, so this is where the real part is 0, the imaginary part is 0. And so Z is going to start off here, but then by computing the square and plus C, well, then now Z is going to get shifted over to wherever C is. It's not important, but in any case, so that's the new value of Z. Now we reapply the function. What's going to happen when we reapply the function with C? You get what? You get C squared plus C. Well, where does that go? Depending on C, we have no idea. But some of the points, right, that start off in the middle of this black region are going to get sent somewhere else, also in this black region. And then you apply the function again, and it gets sent somewhere else, and you apply the function again, and it gets sent somewhere else. And basically, for certain values of C, right, for certain initial choices of C, and with Z always set initialized to 0, when you apply, they just stay bounded inside of some neighborhood around here. They just keep bouncing around inside of a neighborhood. Those points we will color black, right? So that's what the black pixels are in the Mandelbrot picture. Black pixels are the ones that correspond to complex numbers that just bounce around and stay inside of this bounded region. But the colored pixels, those are the ones where you pick a pixel here, and you apply you start off with Z here at 0, but you apply the function, it gets sent somewhere else, and then it gets somewhere else. And what happens for the pixels or the points that are in the colored region is they actually start flying away from the origin. They start right, rather than bouncing around and staying in a constrained region, they actually start flying off to infinity, basically, or out away from 0. So that's what the colored regions are. And the regions are colored according to just how fast they fly off to infinity. So that's how the colors get determined, is how many steps until they leave some bounded region. So we're going to compute these somewhat roughly, right? We're going to use some approximations and stuff like that. This is not going to be mathematically perfect, as nothing ever is mathematically perfect when you are computing, but in any case, so that's the rough idea. That's the Mandelbrot set. We are going to be basically drawing the Mandelbrot set. And we're going to be using those ppm pixel maps that we've been using in several assignments up to now. The problem already sort of asserts that we are going to let the x values vary from -2 to this 0.47. These are values that are just, if you already know what the Mandelbrot set is, then that taking x no less than whatever it was, -2, and no bigger than 0.47 captures the most interesting part of the Mandelbrot set. So there's like no reason to constrain yourself to this region, except that you have to constrain yourself to some region because, again, these are finite computers and they're not going to be able to do infinite space. So you pick the region that you already know contains the most interesting part of the Mandelbrot set. And likewise with the range of y values, right? So we know that our values are going to stay within those regions. By the way, we're going to decide that a point off to infinity, right, flies off to infinity if I guess what, this is probably the magnitude or the absolute value of the complex number. We'll talk about that later. But if that is bigger than 16, I guess, then we are going to say that the point went off to infinity, right? So as soon as the point goes farther than 16 in absolute value, then we say that it's going off to infinity. Anyway, the rest of this basically gives you an algorithm for how to take each row and column of a pixel map and compute the updated values of z, count up the iterations. If the number of iterations, right, the whole time checking to see whether or not with all of the iterated applications, within some upper bound on how many iterations we do this, we keep checking to see whether or not the point flies off to infinity. If at any point the number is bigger than this, oh, interesting. I thought it said that, oh, yeah, someone must have changed their mind because up here it says 4 times 4, down here it says 2 times 2. Should be a somewhat arbitrary choice, but in any case. But, the important point is that we keep bumping up the iteration counter. If we ever, hit max, then we stop trying and say that the point never flew off to infinity. But if it ever does, right, if this condition ever is satisfied, then we say it did or does fly off to infinity. And so basically down here, what's going on is we perform a check to say, well, look, if iter is less than max, then we must have exited this while loop simply because the point flew off to infinity, essentially. And so if the point flew off to infinity, then we color the pixel according to some palette of colors that we've determined elsewhere. So that's a point that flies off to infinity. But if it did not fly off to infinity, then we will color the pixel black. And then we'll write all this data to a pixel map that then gets written to a ppm file. The palette is basically just colors chosen at random, so that's all I'm going to do. I'm just not interested in being fancy about this. So there's a description of the big idea of this project. And so here they say that they're going to use the getOpt function to get optional command line arguments from the user when you run the program. And these are all of the available optional command line arguments. I'll go ahead and show you that. I've already got the solutions to everything here written up, but so I'll show you this. So this is the single Mandelbrot file. You have to include all these things. And so we get basically like a timer and we record the time. We initialize some values of variables. And then here we process optionally provided command line arguments. Print a little info to the user before we then go into computations. And I guess I might as well, since I'm here, go ahead and show you. So this is just truly, well, not truly, but getting a pseudo-random number so that I really randomize, or at least give the impression of randomizing the color palette. I go ahead and get myself right, we are told to use as many colors as there are max iterations. So that's what I'm doing here, right? I am malloking, well, maybe I shouldn't talk through this too much because that's for later. Well, I'll let you read through this if you want to, but the important new-ish things are, I think, basically the time. Oh, by the way, I simply, in the read ppm file, I simply carried over my solutions to read ppm and write ppm that I was using in assignment 6. But then the rest of the stuff is all about using the get time of day and and sort of collecting timer information. This is getting, as we said in a previous video, this is wall clock timing, right? All I'm doing is marking the time when the program starts, marking the time when the program ends, and computing the difference in seconds and printing that. So that is wall time, and that's what I'm printing here. And so I guess an important sort of upshot of all of that is that the runtimes are going to be somewhat dependent on the other processes that my computer happens to be handling at the time. For one thing, I'm running OBS, which is eating up a bunch of resources and is going to slow my computer down when I go to run an intense program. I'm running a browser, which is not a negligible impact on processing speed, and VS Code, which probably eats up a certain amount of memory and processing. So I'm running some not negligible programs, not many, but they're not negligible, and it's going to impact my runtime. I'm also running on what I think is a kind of old and not terribly high performance computer. So lots of things are going to sort of affect the runtime that I observe here. But that's really it. Honestly, the more I think about it, do I really need to walk you through what I've done here? This code here was already here, so you just leave it. And then because a lot of this stuff is really not new, it's stuff we've talked about many times now. I malloc a list of ppm pixels, and I do a for loop for max iterations times. And for each one of them, I construct a color pixel and I put it into the palette. I actually, rather than walk you through the build of this, because it is hopefully fairly familiar, maybe I'll actually just talk you through what I've already built. So anyway, so then the next thing is I also want to have a special thing that I know to be black. So I make this ppm pixel black. And then I make my pixel map, right? So here I'm mallocing ppm pixels, and I'm making as many as size times size, because this is a square grid with dimensions size by size. So right, whatever the user input as the size. So that's me getting the pixel map started. Later on, when the pixel map is done and populated, I'll write it to a ppm file, as we've seen before. But along the way here, I basically just compute. Now, I maybe compute this slightly differently than what it said in the instructions, but it's almost the same thing. I'm just collapsing maybe a few things into a single line that in the pseudocode from the assignment were spread out over a few extra lines, but it's the same idea. And so, right, you can see that I basically just did a nearly one-for-one implementation of the pseudocode that was given in the instructions. This is how, once I know whether or not it flew off to infinity, if it flew off to infinity, then I put the color from the palette corresponding to the number of iterations into that place in the pix map. And otherwise, I put black there, and then I write. I guess this is so slightly interesting because I am using get time of day. And notice when you're using get time of day, I started off up here, you need to declare a struct time val for the time that it starts and the time that it ends. And it has to be, right, it has to be a struct time val because you are going to take the pointer to it and hand it over to this function get time of day so that the pointer gets filled with a standard way of collecting this data, and the second argument is null. But anyway, the point is that when you run this line of code, it fills tstart with the time of day when the function was called. Down here, it is very much the same. I just do it to tend, and then I call on these two structs. They have a TV, what is that, time value? I'm just going to guess, in seconds. I compute the end minus the start. That is my value of the timer. I could try to get more precise than that, but I just don't think that's very interesting. So I simply print out the difference in seconds and then return. So there you have it. Rather than walk you through the build process, since nothing much is new here, then I think I'll actually just leave it at a talk through of this already built code. And so in the next video then, I will, again, right, the plan is to read the book enough so that we could come over here and implement multi-Mandelbrot. In fact, maybe since I like to show you the code in case you don't want to hear me blabbing on, and you just want to see the code and the solution in case you're trying to make these solutions on your end, and you just want to cut to the right, like you're stuck or something like that, and you want to see a solution. Here, let me just show you the code. So without explaining it, here is my solution for multi-Mandelbrot. So there you have it. I'll actually build this in front of you in a future video, but there is the final product that I came up with for this assignment.